Under normal conditions, our products use information from GNSS satellites to control any drift in the Inertial Navigation System, or INS for short. However, in environments where satellite signals are interrupted frequently or blocked for extended lengths of time, a wheel speed input can help to reduce drift in the system. It does this by providing the INS with another independent reference. Configuring a wheel speed input in navconfig is quite easy. All we have to do is describe where the measured wheel is in relation to the INS and how many pulses there will be per meter travelled. When selecting a wheel, bear in mind that you cannot use a wheel that steers, because the system makes some assumptions based on the fact that it won't steer. Also, when sourcing a speed signal directly from a vehicle, make sure it is measured from a wheel and not from the gearbox. Gearbox generated signals won't work because the speed output is actually split between two wheels. Many people acquire a wheel speed signal using an encoder similar to this one. The INS will accept any TTL level signal and considers less than 0.8 volts as low and greater than 2.4 volts as high. The maximum signal input voltage the INS can handle is 12 volts. So let's go through and configure a wheel speed input. In this case, we would say the wheel is about 0.95 meters behind the INS, 0.75 meters to its left, and 0.9 meters below. We're going to leave the default accuracy set to 0.1 meters, even though we're confident we measured accurately. The final step is to tell the product how many pulses to expect per meter. At first glance, working this out can appear tricky, but there is a very simple way. First of all, we need to know how many pulses the sensor will generate in one full revolution. In this case, it's 100. Next, we need to know the rolling radius of the wheel. That's easily found by measuring from the center of the wheel to the ground. In this case, it's 0.295 meters. Now, simply divide the number of pulses per revolution by the rolling circumference in meters. Converting the rolling radius into a rolling circumference is simply a case of using 2 pi r. In this case, that gives a rolling circumference of 1.854 meters. And dividing that into the number of pulses tells us there will be 54 pulses per meter. Again, the system uses our data as a starting point, which it then refines in use, so the 10% tolerance here is okay. And that's it on the options page. Don't forget there are links to all our videos on the support website, which can be found at support.oxts.com.